This first one, now, central limit theorem. Of course, I use a very large number here, 65 times. So 12 fair dice are thrown and x denotes the number of sixes obtained. Okay? So you have 12 fair dice. Every time you throw one, you have got 6 sixes here. So let me illustrate this for you. So you have binomial. This is binomial, right? Because 12, whether you have a 6 or not, is 1 over 6. Every one time you throw 12, voila! Then you throw on the floor 12 dice. Da, 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 da. You count the number of 6 you have. Okay, this is one observation. So if 12 dice are thrown 65 times, you repeat lah. Like basically you're a gambling addict, you just keep doing it 65 times. Estimate the probability that the average value of x, right, means you want x1 plus x2 plus x3 all the way to x65 divided by 65 is less than 1.8. This is what they're trying to say. The average value means the mean value, like that. Okay, meaning you start off with one time you play, one time good one, x1. Then x2 you do the same thing, which is x2 is also binomial 12 and 60. Then x3 is also binomial 12 and 1 over 6 and so on until 65, you know. Okay, and you want the estimate. The keyword here is estimate and the average value. This will trigger CLT. Okay, just take note of that. Now, then how do you estimate? Of course, if you want to find the average value for a binomial distribution, I know some of you will think about, oh, there are 65 times of 12. Then if I want less than 18, then you just go and calculate. But you can't do that because now you're told to estimate. So you need to use CLT. Okay, you need to use CLT. So since we need to use CLT, since n equals to 65 is large, okay, by central limit theorem, we got the license to kill. We got the license to do this. Bar x normal would be expectation of x, variance of x over 65 approximately. Okay, so actually the approximately will becomes, it's quite a good estimate. So this is central limit theorem. You can just use this one here. Okay, now why this is important? I'm like a broken tape recorder, because the distribution that we learn, all distribution that we learn have got mean and variance. We always want the mean and the variance. It's usually defined as the mean and the variance of x. Okay, this x here is one independent observation. So just remember, it's the means of means. So imagine you just you take a sample of 12 and 12 and so on, just keep doing it. Okay, the population would then be the number of dice you can throw infinitely many times. So expectation of x would then be 12 times 1/6, which is actually n times p, which is what? Which is 2. Variance of x will just be 12 times 1 over 6 times 5 over 6. That will be 2 times 5 over 6, which is actually 5 over 3. So very quickly, we can actually write down x bar is 2, and this is 5 over 3 over 65. And the required probability, the sample mean we need less than 1.8. Okay, that is our license to kill. So key in calculator, I presume you know how to key in calculator here. So I also hope that I get the correct answer here. So here, we're just gonna do normal CDF, lower negative 10 to the power 99, upper would be 1.8. Then this mu would be 2. square root ta-da 0.106.